Hello viewers, welcome to this session. In this session, we talk about the applications of total derivatives to find the derivative of implicit functions. In mathematics, functions play a fundamental role in describing the relationship between variables. Among these functions, implicit functions hold a unique place. Unlike explicit functions, where one variable is typically expressed explicitly in terms of another, implicit functions define relationships between variables implicitly through equations. This implicit nature introduces both challenges and advantages in understanding and manipulating these functions. Explicit functions are defined explicitly in terms of one variable as a function of another. For example, y is equals to x squared minus 5x directly expresses y as a function of x. On the other hand, implicit functions are defined implicitly through equations involving multiple variables, where the dependent variable is not isolated on one side of the equation. A simple example of an implicit function is the equation x squared plus y squared is equals to 4. This implicitly defines the relationship between x and y, but none of this is made the subject. In general, an implicit function is a function that takes the form f of xy is equals to a constant. So consider a function z, which is a function of two variables x and y. Then the total derivative can be expressed as dz is equals to the partial derivative of z with respect to x times dx plus the partial derivative of z with respect to y times dy. If we divide both sides with respect to x and simplify, we can get dz dx is equals to the partial derivative of z with respect to x plus the partial derivative of z with respect to y times dy dx. But remember, z is equals to f of xy, meaning that we can replace z here and there with f of xy, so that we get this expression, equation 3.4. Now, if we consider a special case where z is equals to a constant, then dz dx, when we differentiate z with respect to x, we get 0. So that from this equation, we can replace dz dx here with 0, and we get 0 is equals to the partial derivative of f with respect to x plus the partial derivative of f with respect to y times dy dx. From this expression, see that we have the partial derivative of f with respect to x plus the partial derivative of f with respect to y times dy dx is equals to 0, from which we can write the partial derivative of f with respect to y times dy dx is equals to minus the partial derivative of f with respect to x. And from here we can get dy dx, which is minus the partial derivative of f with respect to x divided by the partial derivative of f with respect to y. So in this case, this expression can be used to find the derivative of an implicit function. Let's take an example. We have this explicit function where the function f is given by x squared y plus 2xy squared minus y cubed plus 4x. So that this one is of the form f of xy is equals to 0. So all that we need is to differentiate f partially with respect to x and partially with respect to y. And remember, this f is a function of x and y. It is not just f, it is f which is a function of x and y. So if we differentiate f partially with respect to x, we get 2xy plus 2y squared plus 4. And differentiating f partially with respect to y, we get x squared minus 4xy minus 3y squared. Then we have dy dx is equals to minus the partial derivative of f with respect to x divided by the partial derivative of f with respect to y. Meaning that we just take this expression, divide by this, and multiply the result by -1. This will give us the derivative of the implicit function. We have a second example, x squared y squared plus 2xy. We have x squared y squared plus 2xy, then plus x squared minus y cubed is equals to 0. So our function here, f of xy, is equals to x squared y squared plus 2xy plus x squared minus y cubed. So we differentiate f partially with respect to x. So the derivative of f with respect to x will give us 2xy squared plus 2y plus 2x. And differentiating f partially with respect to y, we get 2x squared y plus 2x minus 3y squared. So that now dy by dx is equals to minus the partial derivative of f with respect to x divided by the partial derivative of f with respect to y. So we have minus 2xy squared plus 2y plus 2x divided by 2x squared y plus 2x minus 3y squared, which is the derivative of the given implicit function. So it is very easy. When using the total derivatives, we just need to identify our function f, then differentiate the function f partially with respect to x and partially with respect to y, then use this expression. Dy dx is equals to the minus partial derivative of f with respect to x divided by the partial derivative of f with respect to y, which will give us the derivative of the implicit function dy by dx. For this session, we end at that point, and thank you for watching. In the next session, we shall look at the stationary points for a function of two variables.